This is the second part of the tutorial 1, which is covering the measurement basics. In the last tutorial, I ended with the basics of measurement, the units and other things, and told you that the next tutorial will be on gas laws. So here it is, the gas laws. Let me remind you once again that these laws, or rather the various equations, various relationships between pressure, temperature, volume, etc. of the gas is very, very important in solving the calculations or numerical problems related to combustion. And combustion being one of the most important chapters in your examination. What we are going to use is the various relationship between the volume, pressure, temperature, etc. along with the mass, of course, and the number of molecules. We are going to learn a new quantity here, that is mole, kilomole, etc. Now, one thing I'll tell you in the very, very beginning of this tutorial, that in any calculations which involves gas laws or gas equations or relationships between various parameters of gas, it is absolutely essential that the pressure should be taken as absolute pressure and the temperature as absolute temperature. Absolute pressure, I told you in the last tutorial, is the actual pressure of the system, not the gauge pressure. And in terms of actual temperature, absolute temperature, it should be taken as Kelvin, not degree centigrade. Please make it the very important point in all calculations related to gas laws. Do not make this mistake. Do not forget to convert the degree centigrade into Kelvin before putting into calculations. Now let's first take a look at the relationship between volume, temperature. That is, what is the relation between temperature and volume when pressure is constant. Now, when I say temperature, temperature is basically the representation of the kinetic energy inside a matter. You know, inside a matter, if you take a very close look, in the microscopic condition, you will see that all the particles are in movement. Now, this kinetic energy, what we see as a representation of this kinetic energy as temperature. Now, naturally, when we take the temperature 0 Kelvin, which is at minus 273 degrees centigrade, it is considered that there is no heat energy inside the system. Since there is no heat energy, there is no kinetic energy, and all the particles will be clustered together at one place. And since the molecule size is negligible, if they are clustered together, then the volume at this temperature will be 0. They are not going to occupy any space practically. This can be also theoretically computed when we bring down the volume at minus 273 degrees centigrade. We find that every matter at this temperature, the volume comes to 0. Now what happens is, when we add heat in this, then these molecules, the particles, they start moving. They get the kinetic energy, and this kinetic energy is represented in terms of temperature. We get some temperature. When we add more heat, the kinetic energy increases, and thus the temperature also increases. What also increases, because the kinetic energy is increasing, the particles are moving farther away, therefore it is covering more space, it is occupying more space, therefore the volume is also increasing. So with the kinetic energy, the temperature is increasing, so does the volume. Therefore, the relationship between volume and temperature is proportional. Volume is proportional to temperature. When the temperature increases, volume increases. We can write it as V1 by T1 is equal to V2 by T2, right? Now, let's take a look at the relationship between pressure and volume when the temperature is constant. Suppose there is a volume where I increase the pressure. Since it is gas, naturally, we can physically understand that it is going to be compressed. Therefore, the volume is going to go down when the pressure increases. Therefore, the relationship is with volume and pressure. When pressure increases, volume decreases. Therefore, V is inversely proportional to P. Therefore, PV is constant and P1 V1 is equal to P2 V2. We can combine these two conditions, which is represented in combined gas laws, where both pressure and temperatures are variable, both are varying. Then the relationship can be written as PV by T is constant, or P1 V1 by T1 is equal to P2 V2 by T2. Please understand, this relationship at two different pressure and temperature to different volumes, which are related in this way, can be very quite often used to correct the volume with a particular change pressure and temperature. That is, basically the temperature and pressure correction to a gas volume or the density can be given by this. We can take a look at an example for this. Let us see. A certain gas occupies 3 meter cube at a temperature of 150 degrees centigrade. Now the pressure of the gas is 7 bar. The gas expands in such a manner that the volume becomes 9 meter cube when the temperature is 10 degrees centigrade. What is the pressure of this gas at this condition? So there are two different conditions, two different temperatures, two different volume. One pressure is given, the other pressure is not known. Let us first write down what is given. So volume 1 is given, that is 3 meter cube. Temperature at that condition is given 150 degrees centigrade. Pressure is given as 7 bar. The next volume, in the second condition, the volume 2 is given as 9 meter cube. Temperature is given as 10 degrees centigrade. And they have asked us to find out the pressure. Now first thing, as I already told you, that in any gas calculations, the temperature has to be changed from degrees centigrade to Kelvin. Therefore, 150 degrees centigrade becomes 423 Kelvin and 10 degrees centigrade becomes 283 Kelvin. In terms of pressure, we can assume that the pressure is given as absolute. If it is given in bar, you can always assume the pressure is given in absolute. It is not going to be a bad idea to write it on top of your paper when you are solving the question, assuming the pressure given is absolute, right? Then you can just simply use the equation or relationship P1 V1 by T1 is equal to P2 V2 by T2, right? Put the values and you get the pressure 2 as 1.56 bar, right? So this way, I have shown you how the pressure is, when the pressure is unknown, it can be calculated. Similarly, if the volume is unknown, that means when we are putting the pressure and temperature correction, we can use the same equation and get the volume in the second condition. Now, let us take a look at the relationship between volume, temperature, pressure as well as mass. In the previous two relationship or laws, actually those two are pertaining to Charles and Boyle's laws. We have considered that the mass is constant. But if the mass changes, then we use another relationship, that is PV is equal to mRST. This is known as the characteristics gas equation. Here the PV is the pressure and volume, M is the mass, RS is the characteristic gas constant or specific gas constant which changes from gas to gas, and T is the temperature in absolute. P is in absolute, not need to mention again. The pressure, now please remember, since the RS, as I told you, you can see a kilojoule here, therefore in this equation the pressure has to be in kilopascal. We have to remember this is very important. If you miss it, you're going to make the calculation wrong. Now, another equation is there. You see, in the earlier equation, the characteristic gas constant is different for different gases. But if we take the ideal gas laws or ideal gas equations, here PV is equal to nRT. Here R is the universal gas constant which remains same for all the gases. But now we can see another quantity, and that is N, which pertains to a number of kilomoles of the gas. The universal gas constant value 8.3143, you'll have to remember, therefore you might would like to write it in the reference as I told you. Now the question we need to ask us, or it's very important to understand, that what is kilomole or mole, right? Now let's take a look at mole and kilomole first. Mole and kilomole, actually it represents basically an amount of substance, a quantity of substance. When we say 1 mole, we actually mean a specific number of molecules. Actually, it is an Avogadro number of molecules, 6.023 to 10 to 23. See, the number is not important to remember. You have to remember there is a specific number of molecules together. Like 12 we call 1 dozen. Similarly, 6.023 to 10 to 23 we will say it's 1 mole. And naturally, when we say 1 kilomole, it is 1000 mole. Therefore, the number will be 6.023 into 10 to 26. Now, what is the significance of this quantity? The significance is that it relates the mass with number of molecules. In a gas, the number of molecules and the mass both are very important to know. Now, this particular quantity, it relates the mass with number of molecules. How? If you take 1 mole of any substance, the mass is going to be its molecular weight in gram. Therefore, if I take 1 kilomole of any substance, the mass is going to be its molecular weight in kg. Now, that is the most important thing to remember, right? Now, it's also called, this mass of 1 kilomole is also called a molar mass, and it's usually denoted by a capital M. Like mass we denote by small m, molar mass we denote by capital M. Now, if I would suggest that you have to remember certain molecular weights and its corresponding molar masses, right? Carbon 12, sulfur 32, H2, hydrogen 2, nitrogen 28, oxygen 32. Now, if you remember this 5, carbon, hydrogen, nitrogen, oxygen, sulfur, I think that would serve the purpose so far as BOE is concerned. Now, other things like CO2, CO, SO2, H2O, you can always calculate in terms of C plus O2, CO2, therefore 12 plus 32, 44 will be the mass molecular weight of CO2, and molar mass will be the molecular weight in kg. Now, this is, you see this important relationship, the molecular weight 12, the molar mass is 12 kg per kilomole. The molecular weight is 2 for hydrogen, the molar mass is 2 kg per kilomole. So this tells you the relationship between mass and number of molecules, because 1 kilomole is a particular specific number of molecules. Now the relationship between, as I told you, mass and number of molecules, if I again take a look. For example, if I ask you a question that what is going to be the number of molecules in 56 kgs of nitrogen? So we know that in 28 kgs of nitrogen, there will be 1 kilomole of molecule. So 1 kilomole of nitrogen weighs 28 kg. Therefore, in 56 kgs, there will be 2 kilomole of nitrogen. So what I have done is, I have divided the mass by its molar mass, right? So m by, that is small m by capital M, will be n, that is the number of kilomoles. Now, if I take a look at the relationship between R and Rs, that is the universal gas constant and the specific gas constant. I use the same one, PV is equal to mRST, and the same is equal to nRT. So mRST is equal to nRT, and n I replace by small m by capital M, so it becomes small m RT by capital M, right? Now if I deduct this 2, cut this 2 out, mass and mass, and the T and T also gets cancelled out, right? So what remains is Rs will be equal to R by M, so that is the relationship. Specific gas constant is universal gas constant divided by the molar mass. Okay, so if I know the molecular weight, therefore I know the molar mass, and since I know the universal gas constant, I can find out the specific gas constant of any gas, the molecular weight is which is known to us, right? We can write the ideal gas laws as PV is equal to nRT. I can replace n by m by r, m. So I can write it as PV is equal to m, small m, RT by capital M. Right? So, since R is universal gas constant is known to us. Another way is finding out the Rs of different gases. I told you, if the molar mass is known, we can find out the Rs, specific gas constant. For example, if I ask you that what is going to be the specific gas constant of oxygen? So 8.3143, which is the universal gas constant, divided by the molar mass is 32. I can get 0.26 for oxygen. CO2 I know 44 is the molar mass, so 8.3143 by 44. So 0.189 will be the specific gas constant. That way I can find out the specific gas constant, as I told you, of any gas, the molecular weight of which is known to us, right? But not of air, right? Because air is a mixture of gas, it's not a pure gas. Therefore, we cannot find out the specific gas constant of air in this manner. For that, we have to take some different route. In fact, we can use the same equation, PV is equal to mRST, and assuming, and this assumption I have already told you on the first tutorial, that you have to remember that the density of air at NTP is 1.293 kg per meter cube, or vice versa, I inverse it, the specific volume of air becomes 0.7734 meter cube per kg at NTP condition. So we can assume that, and since it is NTP, we know the temperature and pressure. The pressure is 101.3 kilopascal and the temperature is 273 Kelvin, 0 degree centigrade, right? Now using the relationship PV is equal to mRST, RS will be equal to PV by MT. Since I know the pressure, the temperature, the mass which is 1 kg here, and the volume which is 0.7734 meter cube, I can find out the specific gas constant of air as 0.287 kilojoule per kg. Please remember, if the specific gas constant of air is not given in the problem, you should first calculate it in this manner, right? Okay, now let us take a look at an example. A steel cylinder of 77 liters of capacity contains CO2 at 27 degrees centigrade. Pressure is 110 atmosphere. Calculate the weight of the gas, the mass of the gas, you can say, contained in that steel cylinder. Okay, now what is given here? They have given the volume, of course, in liters, and we know that 1000 liters is 1 meter cube, therefore 0.77 liters will become 0.077 meter cube. They have also given you the temperature, 27 degrees centigrade. We know to convert it to absolute, that is Kelvin, is absolutely essential. And they have also given the pressure as 110 atmosphere. We know that in PV is equal to, if I want to find out the mass, I'll have to find out the equation PV is equal to mRST. And in PV is equal to mRST, the P has to be in kilopascal. Therefore, I convert the pressure 110 atmosphere into kilopascal. This also I have discussed in the first tutorial, how to convert any pressure, any unit into kilopascal. So we get this much kilopascal is the pressure, okay. They have not given us the RS of CO2, but they have told it's the CO2 gas, and the molecular mass of CO2 is known to us. Therefore, we can find out the RS of CO2 as R by M. So we find it as 0.189. Now, simply using this relationship PV is equal to mRST, we can find out the value of mass, right, which is coming to 14.65 kilojoule. In this example, what can go wrong? One thing definitely can go wrong. If you forget to convert the temperature from degree centigrade to Kelvin, the whole calculations will go wrong. Okay. Now, let us take another example. Here, what is given? The pressure of a gas supplied to an engine is measured as 100 millimeter of water gauge. Now, they have given it is in mmWc. And since they are measuring the water gauge, that means it is measured by manometer. And we know that manometer gives you the gauge pressure, right? When the barometer reads 756 mm of mercury, now I told you that if they mention the barometric pressure, you'll have to take that. Otherwise, you can assume it as 760 millimeter of mercury. They have mentioned it 756 millimeter of mercury here. Determine the volume of 1.5 kg of the gas, the mass is given. If the temperature is 85 degrees centigrade, and the gas constant of the gas is 0.686 kilojoule per kg. Therefore, they have given you the specific gas constant. We straight away can use the PV is equal to mRST equation. What they have given? M they have given 1.5 kg, fine. They have also given the temperature, convert it into absolute Kelvin, right? They have given you the pressure, but they have given you the pressure in two parts. One is the gauge pressure, another is the barometric pressure. The gauge pressure they have given in 100 mmWc. Since the barometric pressure is given in mmHg, I convert the WC into mmHg. Since water and mercury is 13.6 times heavier than water, so whatever mmWc I get, I divide it by 13.6, I will get the height in mercury, right? They have also given the barometric pressure as 756 mmHg, therefore the absolute pressure we calculate as the barometric pressure plus gauge pressure, convert it into kPa from mmHg. So for that I have to divide it by 750 and multiply it by 100. 750 dividing by 750 will give me the pressure in bar, and multiplied by 100 will give me in kP, right? So the RS is also given. What is the volume quantity, right? So using the PV is equal to mRST, V is equal to mRST by P. Therefore, I get the volume as 3.62 meter cube. So it's basically very simple calculations. Here you can see that only problem you might have is the conversion of this pressure into kPa. If you forget that, then it's going to create trouble for you. Okay, now there is another very important relationship, gas equation, which is Avogadro's gas principle, or as Avogadro's gas hypothesis also it is sometimes called. If I take the same equation as PV is equal to nRT, which is the ideal gas laws. Now I consider that there are two different gases, which is, let us take the combustion gas, flue gas. We know that it's primarily nitrogen, the flue gas composition, and there is definitely, there will be CO2, there will be CO, there will be SO2, there will be some amount of H2O, there will be possibly a little bit of CO also, as I told you. Now, let us take the two gases. One is CO2, another is N2. And in the combustion gases, both are having same pressure and temperature. So, the pressure and temperature on these gases are same. But the quantity, if I think about the quantity, quantities are different. In fact, nitrogen is much more as compared to CO2. So let us assume the nitrogen is having about N1 kilomole, which definitely will occupy more space, therefore the volume is V1. CO2 is having N2 kilomole and the volume occupied by CO2 will be V2. Now if I apply the PV is equal to nRT for both the gases, it will become PV1 is equal to N1RT and PV2 is equal to N2RT. P, R and T remains same for both the cases. Pressure, temperature constant for both the gases. R is a universal gas constant, therefore definitely is same for both the gases. Now algebraically, if I divide these two equations 1 by 2, I can cancel out the P, R and T from both the sides. Therefore, the equation will become V1 by V2 is equal to N1 by N2, which tells us that the volume is proportional to the number of molecules when the pressure and temperature are constant. Or I can also say that if N1 is equal to N2, V1 is equal to V2 when pressure and temperature is constant. Excuse me. This is also known as the Avogadro's gas principle, which tells us that under the same conditions of pressure and temperature, equal volume of any gas will have the same number of molecules. Now I can use this hypothesis to get a very, very interesting relationship. Okay, somebody has taken three gases, let us say H2, N2 and CO2, and this thing has been done under NTP condition, normal temperature pressure condition. They found out that the volume of 2 kgs of hydrogen is 22.4 meter cube. Now, what is 2 kgs of hydrogen? We know that 2 kg is the molar mass of hydrogen. Therefore, the number of kilomoles will be 1, right? So, in other words, I can say that 1 kilomole of hydrogen occupies 22.4 meter cube at NTP. So, at the same NTP condition, if I take N2 and CO2, I can very easily write that 28 kg of nitrogen will occupy 22.4 meter cube and 44 kg CO2 will occupy 22.4 meter cube, because what is common between 2 kg hydrogen, 28 kg nitrogen and 44 kg CO2 is all three of them are having 1 kilomole of molecules, right? So as the number of molecules are same, the pressure and temperatures are same, the volume has to be same as 22.4 meter cube. So this gives us a very, very useful relationship. I can find out, or I know the density of any gas at NTP condition, the molar mass of which is known to me. If I know the molar mass, I know that amount of mass will occupy 22.4 meter cube at NTP. Therefore, I know the density of that substance at NTP. Okay, I can use this relationship in this example. Let us say a cylinder of nitrogen is occupying is having a volume of 0.075 meter cube. It contains the nitrogen at 7 bar pressure. The temperature is ambient, 30 degrees centigrade, let us say. What is going to be the mass of nitrogen in this cylinder? The first thing what I need to do is this volume 0.075 meter cube at 30 degrees centigrade and a pressure of 7 bar. Let us convert this to nm cube. That is what is going to be the volume at NTP condition, because keeping the mass same. Okay, so I use the relationship as P1 V1 by T1 is equal to P2 V2 by T2 to give the temperature correction. Here I can say the P1 is 7 bar, the V1 is 0.075 meter cube, the T1 is 30 degrees centigrade, which is this many Kelvin, 303 Kelvin, and I convert into NTP, therefore 1.013 bar. This was his bar, so this I have to keep in bar, and the temperature is 273 Kelvin. What is going to be V2? V2 comes out as 0.467 nanometer cube. That is at NTP condition. Now I use the same understanding that at NTP condition 22.4 meter cube of nitrogen will have a mass of 28 kgs, right? Therefore 0.467 meter cube of nitrogen is going to have a mass of 0.584 kgs. This is the way I can use these equations. Now I told you now in the video tutorial 1 part 2 about the relationship between pressure, temperature and the volume as well as the mass. We are using the equations P1 V1 by T1 is equal to P2 V2 by T2 and PV is equal to MRST and PV is equal to NRT, and I specifically told you to remember that the kilomole, the significance of kilomole, that 1 kilomole of any substance will have a mass of its molecular weight same as its molecular weight in kg, right? So with that I am concluding this session, this tutorial. In the next tutorial I am going to talk about the properties of steam, right? So therefore before you attain that tutorial you must have a steam table with you in SI units, right? And it's not going to be a bad idea to practice on the examples given in your chapters, any examples on gas laws, using gas laws, right? Particularly you memorize the various molecular weights and molar masses as I indicated, the carbon, hydrogen, nitrogen, sulfur and oxygen, this 5, right? And let me tell you one thing, that if you can master the gas laws calculations, the combustion calculation is going to be very easy for you, right? With that I would say goodbye to all of you. Thank you.